Okay, good morning. Today we're going to be talking about latent growth curve modeling, and I'm going to run a couple of models. I think I have one that's a continuous variable and one that's I believe it's an ordinal variable, but it could be some kind of discrete variable. But we'll be talking about that. First out, the way I'm always trying to think what's the best way to present all this information. I certainly can just talk about it, but I did write a couple of papers where I used I used where I described latent growth curve modeling in detail because I was doing a comparison of area under the curve as a method of assessing longitudinal data, right? And I compared it to latent growth curve modeling, generalized estimating equations. What else? I think I repeated measures ANOVA. So I thought, well, obviously I have to describe them. So I think it might be best for me to read some of my own work. So this is again, just to be clear, this is page 678, just so I remember this is my paper, right, that I wrote for in Stats and published, just so you know that, I'm not, you know, trying to sell you something bogus here, that I didn't do it, but I did it. Okay, so let me go ahead and just get started. So I'll do a little bit of reading and I'll interject. This is what I did last week when I discussed structural equation modeling using one of my chapters in my book. I also have chapters that cover this, but it's better that, this is more current actually, I think, than the chapter. So LGM, I call it latent growth curve modeling. Some people call it latent growth modeling. Some people call it growth curve modeling. The idea is it involves latent variables. It is a structural equation modeling method, and it involves estimating individual developmental trajectories. So trajectories change over time, but we're looking at each individual's developmental trajectories, and we're measuring it from repeated measures of some observed variable. So whatever the variable of interest, we might be interested in, say, change in depression, and we'd like to predict that. So this is really involving our dependent variable, right? So LGCM uses latent variables, as you know from the SEM lecture last week. Uh, these are unobserved variables. It uses those to model the initial level and the rate of change from baseline. Okay, so again, latent variables are unobserved. They're only known through their indicators, right? And like one of the indicators is baseline level, and the other is rate of change from baseline. And we can model this trajectory as either linear, quadratic, or whatever we want, right? Uh, so we'll start, of course, with a linear one. The basic growth model includes one latent variable for baseline, and I'll show you a figure in a second, and an intercept for the baseline intercept, and one for the linear trend. Again, sometimes talking about a basic model with just two latent variables, one representing intercept and one representing rate of change from intercept. So using matrix symbols, the t repeated, so we have t, let's say t equals time. So the t repeated observed measures are regressed on the set of latent variables representing the initial level and rate of change, along with the residual variance not accounted for by the model. You can see that in equation 7 here. So we have some outcome variable, or in this, it's a vector of outcomes because we have more than one. Like here, we have more than one outcome with 4 different time points, right? So it's a vector, right? A vector is like a matrix. Like this is a 4 by 1 matrix. That's a vector, right? And then we have it related to the latent variables by these factor loadings, like we did in factor analysis, factor loadings. And then we have the error here. So we have this lambda, eta sub I, and epsilon sub I being the error. And it's really important that you know what these symbols are because it makes it easier. So this is a lambda, and this lambda here, right? So first of all, the y sub I is a vector, right? It's some kind of a vector. And then say we see it's a t-dimensional vector because there's 1, 2, 3, 4 time points, and its dimension is 4, right? It's 4 by 1. And lambda is a t by m matrix relating the m latent variables. So in this case, it would be 4 by 2, right? Because there's four. Oh, here it is, right? 1, 2, 3, 4 variables and two latent variables, an intercept and a trend latent variable. So it's a 4x2 matrix, right? 4x2 matrix. Where was I? Where did I leave off here? Yeah, here it is. Right. And by matrix relating the M latent variables eta, those are the latent variables. This is a symbol eta, right? The eta vector to the T repeated measures epsilon. T repeated measures, epsilon is a T-dimensional vector of residual. So that's the leftover, the ones that we saw that before when we were doing SEM last week, or even when we were talking about exploratory factor analysis. There's always going to be leftover residual that's not accounted for by the latent variables. Equation 8 is the structural part of the model. We talked about a measurement model versus a structural model. So a structural model can be used to regress latent variables on other latent variables or unmeasured variables as well, right? So alpha in this equation 8 is a vector containing intercept parameters relating the predictor variables to the latent variables. So in this case, we have like two latent variables. Beta is an M by M matrix of parameters from regressing latent variables on other latent variables, which are possible. So you could do that. I mean, I do that a lot when we are comparing like growth in two different processes. Like say, we used to do a lot of cigarette smoking and physical activity. Does rate of change in physical activity influence rate of change in smoking or something like that? So that's something we call parallel processes or associated processes, latent growth curve models, right? Gamma is an M by P matrix of regression coefficients relating the P predictor variables, or we can call covariates, if you want X, so this is it right here, right, to the latent variables. So we might have predictors of the latent variables. They could be whatever, right? It could be any kind of thing, predictors. And sigma, in this case, not like it's another kind of sigma. Sigma is an M-dimensional vector of residuals. So these are different residuals, right? Residuals for the latent variables. These are residuals for the observed variables. If we expand upon equation 7, see, I love writing this kind of stuff. It's so much fun. We expand upon equation 7 with T equals 4 time points, right? Here it goes, right? Time points and a linear trend factor and use matrix algebra, right? So see, one thing that I do when I write is I want to explain everything so clearly so nobody is confused, right? A matrix is defined by its rows and columns, right? Addition is cell to cell, right? We've done that in class. I think I showed you how to add matrices together for equally sized matrices of the same dimension, like 2 by 2, 2 by 2. For multiplication, the inner terms must be equal. And this is what I mean by this. So for instance, this is a 2 by 2 matrix multiplied by a 2 by 3 matrix. The twos are the inner terms, like 2 by 2 is the outer term. This is the outer term. 3 is the outer term here. 2 is the outer term here. So this is 2 rows by 2 columns. This is 2 rows by 3 columns. But the inner terms must be equal. The columns here and the rows here. And then the product would be a 2 by 3 matrix. So the outer terms represent the dimensions of the new matrix. Okay. So yeah, yes. So this is what we obtain when we do like a product here. Yeah. So you're seeing the product here between these two, right? And then you have addition and all. And this is our beautiful equivalent of equation 7. So note, I'm just looking at these nice notes that are here. Note that y sub I represent the y sub I, these are these little guys here, represent each individual's outcome score. So this is just a way of organizing data. That's what makes matrices so cool. But not only that, then we can represent them as equations and do work on those matrices, right? Rather than having to work on individual values. That makes it even more cool, right? So these represent individuals' outcome score on given repeated measures. Here, the pi's are the latent variables. So you have the pi sub 0 sub I. So it's it's an individual's latent variable score on the intercept and then on the trend as well, right? Okay. So this is basically telling us what individual i's trajectory looks like. So this is my trajectory, right? Expanding upon equation 8 with four measures, with four measured predictor variables. So I have some four predictor variables, whatever they may be. These are predictor variables of some sort, right? Predictor variables as in the present analysis. So what I did here was the analysis I did for this study, and I did a simulation study for this one. If you want to read this paper, you can. And no latent predictor variables excluding. So that's why in this case, I don't include this term right here because I don't have any latent, any modeling from latent variable to latent variable. So we exclude the second term. So, but we can expand upon this, and this is what we get. We get the intercept, and then we get the slope factor, and we have some kind of an intercept itself for these gammas, right? So here, right? So we get these gammas, and then we get also these, I guess these slope factors for the uh, for the predictor variables, right? So we get this here. We get for instance here in this case we're looking at the intercept only. So we have the intercept latent variable. It has its own intercept for the regression of these predictor variables onto that latent variable, and then you have the slopes for each of these predictor variables, which is x1 sub I, x2 sub I, x3 sub I, x4 sub I, and so on. And then it has its own sigma here as its error term. Pretty cool, huh? Okay. And here's a picture of what I was showing at this place, right? Here's a picture that shows what a latent variable looks like. And this comes from that model. So you could actually go back here and use this model, use these equations to understand this figure, because here's your baseline level and how it relates to each of the four different observed measures, right? And then here we have a linear trend that relates to the different observed measures too. And you'll notice in this case, what we did was we modeled a linear trend. So we're assuming that rate of change is linear, like a 1 unit change in time represents a 1 unit change, 1 unit increase in this whatever in the dependent variable, right? So it's just growing at a linear rate, not in quadratic or anything like that. But we have a baseline value for intercept here, and that the relation between this baseline level and the different time points remains constant, right? It's always one because it's baseline. Baseline doesn't change. However, the linear trend, of course, will have it'll change in a growth fashion, a linear growth fashion. So you got 0, 1, 2, 3. So we're fixing the factor loadings. You recall when we were doing exploratory and even confirmatory factor analysis, you get different factor loadings, but you're estimating them. But here we're fixing them. Right? They have to be fixed because that's how we demonstrate growth. This one, the linear trend, the arrow from the linear trend to y1 is set as 0 to make sure that we know that this is our intercept. Okay, so that's basically what a latent growth curve model is. And like we did with other structural equation models, we judge them using fit indices. We use basically the same ones. We use the CFI, the square root mean square error approximation, and a couple others. And the same criteria apply as they did with structural equation modeling. Okay, so we'll talk a little bit more about this. And so if you're interested in this article, it's on our class site. If you're watching this and you're not in one of my classes, this is area under the curve as an alternative to latent growth curve modeling when assessing the effects of predictor variables on repeated measures of a continuous dependent variable. So that's the citation. Here it is actually. Citation, if you're interested in it, right here is a 2023 article in the journal Stats. Okay. All right, let's go and let's run some analyses first. We're going to first do it with a continuous outcome variable. So Mplus, as I mentioned last week, has a free download if you're interested that allows you to model 6 dependent variables. So that would be more than enough to run what we're doing here. So what we're going to do in steps is we're going to just go through this process. First, you needed to download this data set. I call it LGCM dot. This is their downloadable programming matrix, programming file, right? So this is the programming file. So I actually downloaded that. Go under Mplus. Now I have a full version of Mplus. Let's see, this is unconditional model. I was going to do a couple things with it, but one thing you can do at first is just run the basic, right? The uh, analysis equals basic if you want just to see what the variables look like. But I did that last week. You don't really have to do that now. Let's get straight to the analysis itself. So I created a data set that has some variables in it that we can use for this analysis here, right? And this is a latent growth curve model. And I said an unconditional. So an unconditional model would have no predictors, that there are no variables predicting the latent variables. You can also actually predict the measured variables too, if you want. With I mean, you can do a lot of different things, but that's a little bit more complicated than what we're doing now. But our goal is to eventually make predictors of latent variables, like what's the predictor of intercept and what's the predictor of rate of change, right? But the unconditional model has no predictors, or some people like to call this the crude model. So that's what I would start first. And our dependent variable here is depression, right? In terms of, do we have to assess for normality? You assess for multivariate normality. You don't assess for univariate normality. Okay, so like you'd use Mardia's coefficient. I know in SAS you can do that. I think there's like a macro of some sort that you have to, I think there was in SAS. I don't know if I did that in SAS or in SPSS. There was a macro that I think it was in SAS that you had to add in order to get that assessment, right? Because you can test for multivariate normality. You can't visualize it with four different variables. So let's go back to here. Okay, so like I showed you last week, excuse me, there's specific code that we use. This is my first thing. You have to say where the data are, excuse me, file is, and what the location is. I'm using a comma separated variable file, right? So this is something you can get from Excel. You can also, if you don't have a file, if you have something like SAS or SPSS, you can create the data file and then save it in Excel and as a CSV file, and then do whatever manipulation you need there. I have to list the names of my variables in the data set. Names are, so these are, you notice that these are the commands. Data, this is a data statement, I guess, variable statement, and then names are, in this case, that's sex, not Hispanic. Lunch, sensation is in sensation seeking. Lunch was whether or not somebody received free or low-cost lunch. 1 is yes and 0 is no. Anxiety, depression at the 4 different time points, and then also cigarette smoking at the 4 different time points. I set my missing values at 9999 just for sake of sanity. My user variables, so I always have a list which variables I'm using in my analysis, and the ones I'm using are depression 1 through depression 4, and they have to be in order, of course, if I'm going to have this let's use this dash here, right? So this is saying depression 1 through depression 4 because they're in order, right? And then I do my models. Sorry about that. My model says intercept, slope, right? So, and again, if I wanted to have, I could add terms to this. Like if I think that this is not a linear model, I can add a quadratic model and then a cubic model. And I can use whatever I want as a symbol. But I might do Q for cubic, sometimes Q for quadratic and C for cubic, right? I'll just put them after these, and this will automatically do the multiplying to get the quadratic and cubic terms, right? But then I have this bar here. I forgot what I called it. I had it written down, but whatever I call this, I have this little bar here. And then what I do is I set my variables. So they're increasing incrementally depression. And I think, I apologize, I don't know the latest coding, but I think you don't even have to do this. I think you can just list what the variables are and it'll automatically do a linear. I'm not 100% sure. This is version 8.3, so it's not the latest version. I think we're up to version 9, but it's not cheap. And I'm funding my own research, so I buy what I need to when I need to. So I have the intercept and slope latent variables, and then we have depression at time 1, time 2, times 3 by 4, and I set the factor loadings at 0, 1, 2, 3, right? So this represents growth across those 4 time points. Now, I'm setting them there. I could relax these, but then I would lose the whole, linear thing. Like I could say, well, this doesn't look linear, so I say, let's just estimate this instead. So I could actually put that there and this asterisk, and that would allow me to estimate that, freely estimate that. So, but again, if you're interested in, maintaining a linear trend, then you do that. Just ask for some sample statistics, some standardized results, and then some confidence intervals. Okay, so that's what I want. So I'm all set to go, and I just hit the Run tab here. Usually it'll ask you if you change something to save beforehand, and it'll save it. So here I ran the tab. I had a large data set of 1837 individuals, 4 dependent variables, 2 continuous latent variables. The latent variables are continuous. The method of estimation for parameter estimation is maximum likelihood, which is good because it allows me to make comparisons, right? Using chi-square difference tests. Let's see, it shows me what proportion of the data are available. Like for instance, between depression 1 and depression 1, between self, we have 99.6% of all data. There might be some couple missing here. Depression 2 and 1. So there's a decrease as we go along, right? Starting with 900, starting with the most data and then going down, right? Right down to 0.889 in terms of the coverage or proportion that exists in between 1 and time 4. We get some statistics here, like the means, get the covariances. You can have that covariance matrix, that beautiful covariance matrix, and the correlations here. Let's see. Oh, this is what I want to look at then. Okay, let's take a look at our, what we're really interested in is to see if this model fits the data well. Our top criterion for assessing model fit is looking at the chi-square test. So this says, yes, the model fits the data, the variance covariance matrix, or the one implied by our model fits that one, or it doesn't fit one. And this doesn't fit. You see, it's a significant chi-square. So it's saying, yeah, there's some misfit somewhere. Some people will argue that that's because of the large sample size, everything becomes magnified, but then others will argue, well, it's misfit is misfit, and this just does a better job at pointing it out. That's for you to decide, not for me. But I'll always say that, hey, this isn't a perfect fit. Okay, so we do have misfits, some misfits. So, when I say that, I don't say the data model fits the data well. I'll say the model fits the data fairly well because it didn't really pass this, but it did well with the RMSEA, the CFI greater than 0.95, etc. So I mean, it's pretty nice, right? So and then we get all the values here, right? All the estimates. But really, at this point, and including a correlation between the intercept and the slope, which is not significant, and our means. But what I really am interested in is starting to add some predictors to this model. So let's go from an unconditional model to a conditional model. So let's start adding predictors. And I had a plan. All right. So let's see what my plan was here. Okay, cool. So we ran the unconditional model. Next, add the following variables to the model: baseline smoking, Hispanic ethnicity, and anxiety. All right. So let's do that. Oh, first they said add sex as a predictor variable. Let's just do that only. Okay, so let's add sex as a predictor, or gender, whatever you like to call it. Okay, so let's go ahead. Let's actually use the other one since I already called this an unconditional model. This is a conditional model. All right. All right, so we're going to add these predictor variables. So use variables. So we're also going to use, oops, what did I do there? Hey, pressing wrong buttons on computers. Well, we're going to use sex, all right? And this is a binary variable, and I can't remember which is which. It would be one is female, one is male. We could easily tell because usually females, these are adolescents that have higher depression than males because they report higher depression, not that they're necessarily more depressed. We males are stubborn. So I'm going to add part of this model, structural model now, where we have I, S on sex. This will allow me to make the prediction. So this is model has changed a little bit. Yes, I want to save changes. All right, so did we lose any people? I think we still have the same amount, 1837. We do have one independent variable now. All right. So yeah, models is still kind of similar fit. It's not, we're still looking at these as well. Eventually, that's what you want to report is how well the model fit the data. But we do have these predictors now. Here you go. So sex had a significant effect on the intercept level and the rate of change. So this is saying sex is one is female and zero is male. I know, I mean, I've done tons of research on depression, and this, and I've used this data set before, so we know that females would be one and males would be zero just by looking at this, because they report higher levels of depression. So this tells me that there's a significant effect, and this uses a z-test, which is really cool. Relying on the central limit theorem, right? You can use a z-test here. Okay, instead of a t like you do in regression analysis. And we also have this impact of being female on rate of change from baseline. So there's an increase in the rate of change from baseline, right? So both of these are significant. Okay. All right. So we controlled for sex. So let's keep on adding variables. So the next step I needed was to add baseline smoking, Hispanic ethnicity, and anxiety. Let's say I was interested in primarily in whether or not anxiety affected the, well, even though it would, there should be correlated. I mean, they are pretty correlated. But if that was our primary interest that impacted rate of change, then I would start here, right? But I would control for these other variables first, like sex, baseline smoking, and ethnicity. All right, so let's add these baseline smoking and ethnicity here. Oh, so that would be smoking at time point 1. So I can also I can just add them all here. IS on smoke 1. Well, I should probably put Hispanic before that, right? His not, wait, I call it not Hispanic. So this is not Hispanic, so it's not quoted as Hispanic. These variables can be no longer than 8 characters. 1, 2, 3, 4, 5, 6, 7, 8. Smoke 1 and anxiety, angst. So that's why you pick and choose how you spell these, or how you what names you use. So let's run this. Again, it'll say save change. Oh wait, did I forgot to mention them here. Yes, that I was going to use them. So sex, not Hispanic. There you go. All right, so let's run this. Morning model variables. So what did I do? I did something wrong here. What did I do wrong? Oh, I forgot. I forgot to. I deleted them. So it actually ran the model with these as just being free variables. So I have to put them in here. Well, so now that I mentioned them here, right? Sex through angst, I can actually at this point expand sex through angst. So I ordered them here, right? Right. So see here it was sex, not Hispanic, lunch, sensation seeking. So this would have included sensation seeking, but here I have sex. I did write sex, not Hispanic, smoke and angst. So now I can just add them. I can have this use this dash here and it would cover sex through angst, because it's like based on what I did last. Save this and then run. There we go. So I lost some more people, right? Because I see I have 1820. I think I lost more people. Let's go down. I really, at this point, I might want to get rid of the SAP stat, but it depends if you need them or not. I don't know. It seems like it's a lot of stuff. It was a model, the fit is 89.980. I mean, still not great, not horrible, but not great. And this RMSEA is still like all this is below 0.08. Our CFI is still strong. So, I mean, it's still an okay model, but let's see what, so there's two things you want to do. You want to make sure the model fits the data well, right? Or at least fairly well. And then once that happens, then you go into interpreting the results. Because if you have a poorly fitting model, what's the point of interpreting the results? You want to make sure the model fits well. So let's see what we got here. So again, sex is significant. Being not Hispanic has a significant, well, so it looks like Hispanics actually smoke more at baseline because this is not Hispanic, is negatively related to baseline smoking. To baseline depression. Smoking is related to baseline depression and anxiety. It's kind of what we expected. In terms of rate of change from baseline, sex still increases depression over time, or being female, I should say. Not Hispanic has no effect. Smoking, so smoking is associated with a reduction in depression over time. That could mean a lot of different things, okay? And anxiety also. So this could mean a couple things. It could be some kind of an effect that's occurring, or it could be just like a ceiling effect, right? Because you're so high already that there's not much more room for growth. So it could be kind of leveling off, so slowing up the growth. So that's probably what I see, especially with anxiety, right? One thing to do, this is where you could actually do an associated process model where you're modeling these two processes simultaneously, like depression and anxiety, and you see what happens over time, right? Does change in one continue to affect change in the other? You have your residuals here as well. They're all significant. Then you have the standardized values. I'd use the standardized values for if I drew a figure and I was presenting it, I would use these rather than the non-standardized values. I can make direct comparisons, right? Like which ones are more important, which are most important. I mean, I can make direct comparisons because their scales are different, but when I standardize them, I can say, oh, anxiety is more important than the other ones, right? And similarly here, anxiety is definitely more important than the other ones. Okay, so that's running a model that's has a continuous dependent variable, repeated measures. Let's look at an ordinal one. So I'll go back to the literature since I like reading so much. Is this one that I just showed you? Yes. Yes, I can close this one. Go back to a different article in that series that I wrote. Again, this is looking at area under page 1368. So this is again looking at area under the curve. So this was comparing the relative efficacy of generalized estimating equations, latent growth curve modeling, and area under the curve with repeated measures, discrete ordinal outcome variables. So I did one with the first one I did was with the zero inflated Poisson variable, comparing area under the curve to latent growth curve modeling. Then I did the paper looking at a continuous latent variable, measured variable. This is the one we just covered now. And then this one includes discrete variables. Because one of the things you're going to see is that you have a lot of processes that are discrete, like smoking. Smoking, I mean, if we just counted the number of cigarettes smoked, then you go, oh, well, that's continuous, actually. Yeah. Yes, but well, actually, it's not. It's discrete. It follows a Poisson distribution. That's why I did the first paper. But drug use, you tend to get a lot of people not using, and then you have a few people using. So either you can do this zero, what's called zero inflated Poisson, because a lot of people don't use, they get a zero score, and then the rest seems to be continuous, perhaps following a normal distribution. But what we tend to do is, in many cases, is create ordinal variables for increasing levels of commitment to behavior, like in this case, smoking, right? So in this case, I looked at, okay, well, we can do latent growth curve modeling with ordinal or even binary variables, whatever. And I think with the area under the curve, in terms of the assessment, I compared it to in these three scenarios, but then after that, I stopped with that. And now I'm using it in studies. Like we did a study recently where I used it for measuring social anxiety and a couple of other thing. So now I'm just working on those, and then there's something new I'm doing with area under the curve too, but they'll be out soon. Okay, so let's talk a little bit about 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 latent growth curve modeling with an ordinal variable. So again, I'm going to go back to reading. I'm reading my own stuff. I like reading my stuff, but if I ever make a mistake, it's like, oh crap, why did I do that? That's what I don't like. Many of the restrictions encountered with generalized estimating equations are not met using LGCM with repeated measures of data. LGCM is a multivariate. So this is basically, I'm repeating some of the stuff. I'm also using a little bit different terminology here, different time when I wrote it. LGCM is a symbolism, is a multivariate method that employs, we know that unobserved latent variables, we already know that, to represent rate of change, baseline and rate of change from baseline, right? Equation 4 presents the relation among the latent and observed variables in a prototypical LGCM with ordinal data. So here it is right here, equation 4. So we have y equals v, and these are vectors and matrices here. Just like before, y equals v plus lambda eta plus epsilon. So we see y is a vector of observed ordinal variables, v is a vector of regression intercepts, lambda is a matrix of factor loadings relating the unobserved variables to the vector of latent variable, relating the observed variables to the vector of latent variables eta, and epsilon is a vector of residuals. So it's like we just did before. Equation 5 clarifies equation 4 with respect. So in this study, and this study actually used real data. This wasn't a simulation study. I just took real data from a panel study of income dynamics and let's see how they compare to one another. Equation 5 clarifies equation 4, and here we're using the 3 time points, right? There was 3 different time points because that's what they had in the data. That made sense. So here we have everything working from left to right. We have the vector of ordinal outcome variables for participant I at time point t. So I1, I2, I3, where time t equals 3 time points, right? On the right side of the equation, we have the vector of regression intercepts are set to 0. The lambda matrix includes the factor loadings for the intercept factor in the first column, the slope factor in the second column. So it's a 3 by 2 matrix, 3 by 2 matrix. The intercept, and then here, this is the lambda here. The intercept loadings are set to 1, indicating, as we mentioned before, an unchanged relation between the intercept and the repeated measures. It's interesting. I was reading my textbook and I didn't realize that somebody changed relation to relationship. I say relations are for people, relations are for variables, relationships for people. Learned this in my doctoral program. I've been a strict adherent to that, but sometimes these editors, they change things. They put relationship in there. Those dummies. The unit increasing factor loadings for the second column suggests linear growth over time, right? So we're not suggesting anything else, but we could if we wanted to. The next vector includes the 2 factors. So here's the 2 factors, eta 0 and eta 1. The first representing the intercept, and the second representing the linear trend factor. And you could add more, like if we did a quadratic trend, we could have a third, and then a cubic trend, we could have a 4. Final vector represents the residual, 1 for each time point. Residuals are assumed to be uncorrelated, right? Although sometimes you can release that restriction. And this is one of the things that people do. So I mentioned here it's not recommended. Sometimes people say, hey, my fit isn't very good, right? When you look at the fit of the model to the data, and what they'll do instead is they'll say, oh, well, one way to increase fit is to release this constrained. So right now the correlations are constrained to be 0, right? They're not allowed to correlate, but I could just release them and allow them to correlate, and that would improve my fit. But then that's what we call post hoc model fitting, and that's not really good. The latent variables, we already know that. Oh, yeah, but important things that latent variables are continuous. And this is something that when I first learned about this, I unfortunately didn't understand. So I was talking to people who probably didn't understand it as well. And there's, oh no, if it's underlying a categorical, observed variable. It's a category. You can interpret it in the same way you would a categorical variable. But that's not true. The latent variables are continuous. Okay, so you forget anything about it. And this is an advantage that GEE has, because in GEE I can do interpretations that are things like odds ratios, etc. But you can't do that here because we're dealing with latent variables that are continuous in nature. So we have to kind of deal with that. Now, there may be ways to work through that to make the interpretation better, talking about standard deviations, etc. So, but that's just in terms of they're latent variables and they're continuous. Okay. To capture, and this is really the cool part, to capture progression across increasing levels. So there's an ordinal variable that we have to treat as a continuous variable, right? So how do we do that? To capture progression across the increasing levels of the ordinal variable, LGCM uses thresholds. It has these thresholds, like these walls, right? These cut points, we call them tau. The thresholds are cut points in a continuum representing propensities to progress from one ordinal level, one ordinal category to the next in an observed variable. This is so cool. To assess change over time, these thresholds are constrained to be equal, right? If they remain equal, then if there's progression, it becomes easier and easier to cross these thresholds, right? So, yeah, that's interesting, right? So you can judge progression based on what happens to the relation between the individual and the threshold over time. With respect to latent variables, they're assumed to be multivariate, normally distributed with a mean alpha and a variance, in this case, variance covariance called psi. So we look at equation 6 right here. So we'll say the eta is multivariate normal, and these are its natural parameters are alpha and psi. Alpha and psi, the mean and the variance covariance. The residuals are assumed to be normally distributed with a mean of 0 and a variance of theta. I love all these symbols. By the way, I have this posting of Greek letters right in front of me that I can look at whenever I forget something. Sometimes I forget. So I'm not doing a very deep dive into everything here. I do suggest reading this outstanding work by Maida et al. And Mason. Mason worked with Mutane, who's the one who developed the Mplus software. I think she was one of his students. So there's some really good introductions into working with ordinal data and latent growth curve modeling. But there's also, if you need a general introduction to latent growth curve modeling, you can also see Duncan and Duncan is a good book that you can use. Okay. So this just shows you that the distributions of these variables, okay, these latent variables, epsilon is a latent variable as well. It's not observed. We don't, could be like a lot of different things. LGCM also permits researchers to assess the effect of potential predictor variables on baseline and trend factors. We already know that. In addition, one can assess how changes in another repeated measure variable influence repeated measures on the dependent variable. And we also mentioned that before, this associated processes, latent growth curve modeling. There's some sites, some references. This could involve, for instance, assessing how baseline level in one process influences trend in the second process. You can do trend to trend effects. There's so much you can do with it. It's really, really cool. We represent effects on growth factors. So we sort of did this. We did this in the last one as well. So then just maybe I use a little bit different symbols here. So this is looking at how, say we're predicting some factor. So we have eta, right, is equal to alpha plus gamma psi. Yeah, gamma psi. How do you pronounce it? Psi, psi, I think psi. Yeah, KSI plus beta eta, beta eta plus, and this last one I think is zeta. Yeah, like Catherine Zeta-Jones, zeta. Okay, so alpha is the intercept here, right? Relating whatever these predictors are to the latent variable. Gamma is a matrix of coefficients relating observed predictors to latent variables. We already did this before. Psi is a vector of observed predictor variables. Beta is a matrix of coefficients relating the latent variables eta to one another. And then zeta is a vector of residuals. Do you need to know all that stuff? Hell yes. No, I say I'm not really 100% sure that you do unless you're interested in it at a deeper level like I am. Some advantages of latent growth curve modeling include a likelihood function, so it allows for model comparison. In addition, one can test multiple hypotheses, exploring the effects of predictors to repeated measures of the dependent variable. You can even have predictors that are affecting the observed variables, kind of crossing over the latent variables. You can do like anything. Such a beautiful type of data analysis. It's not the only one that's really great, but it is a beautiful type of data analysis. Moreover, one can assess the effects of initial level and rate of change on other outcome variables, right? Whether latent or observed. Further, like GEE, one can assess change on a variety of levels of dependent variables, whether continuous or discrete. Another advantage of LGCM that's not shared by GEE is how it handles missing data. So GEE, there's an assumption of that missing data are missing completely at random. So that means that all that missing values are a random sampling of the complete data set, and that's not a very tenable assumption because you have missing data, but it's assumed that they're not related to like the predictor variables or any other variables is kind of, it's not that great an assumption. It won't normally hold. LGCM assumes that data are missing at random. This is far more tenable. So it can be related to some covariates. So there may be sex differences in the and missing data, right? Whether you have missing data or not, or even like an earlier instance of the repeated measure could influence missing data on later instances. It uses using full information, FIML, maximum likelihood estimation. Basically, LGCM uses all available data on the dependent variable to estimate the parameters. So that's really cool. So it'll be able to handle, you'll have a larger sample size than you would say with some other methods, like say with repeated measures ANOVA, where you might have list-wise deletion of missing data, and then you have this advantage that we're not assuming uh, what GEE does. Although there are things that you can do to GEE to relax that. Okay, um, that assumption. All right, so let's take a look at an example of how we do this. Again, so go back to our paper here. Rerun the latent growth curve model with smoking as an outcome, repeated measure. Okay, let's do that one. Smoking. So this is now a dependent variable that is ordinal as far as I can remember. We have natural ordering. Well, we'll see that in a second, actually. So let's see, where did I have that? Here it is. All right, so again, I have the same coding. The only difference here is I have an option that talks about my dependent variable. So my user variables in this, call this the crude model again, right? Unadjusted model, I'm looking at these four variables of smoking, and I mentioned that they're categorical. So this will introduce a lot of different things, including estimators, and everything else is the same, right? Intercept, slope, everything else is the same. But I just have to mention these are categorical. So let's run this first. Okie dokie. 1837. So uses a weighted least squares maximum. I think it's maximum likelihood method. I can't remember what the WLSMB exactly stands for, but it changes it, right? It changes it with delta parameterization, right? All right, so again, we have this covariance coverage. We do have four levels to this variable. That's one thing that I like, is that it show you that there's four levels. You see category one here was not, I believe this was just never smoked. I can't remember if it's never smoked. I think it's never smoked and so on. Or this may have been, but it's more likely to have been smoking in the did you smoke in the last month? No. And then yes, you did. And then smokes like weekly and then daily, something like that, right? But the important thing is to show you how there's change. You can see the change. You went from, well, actually, it seems like people were reducing the amount of smoking, but also you had loss of data over time. So it's just interesting to look at it. But let's take a look at the growth. Here's our thresholds. right? Means, intercepts, and thresholds. And thresholds are indicated by this dollar signs. First threshold, second threshold. There's one less threshold than there are categories. So there's 4 categories. There's 3 thresholds. We have to go across one threshold to go from 1 to 2, another go from 2 to 3, and another go to 3, 4. You can convert these into probabilities if you like. So these are the thresholds. So here, so going from 1 to 2 was relatively easy compared from going to 2 to 3. So they're getting higher and higher. It's really hard to go from 3 to 4. That's just telling you that fewer and fewer people achieve those higher thresholds, right? And then you see them as they increase over time. There's a correlation matrix, and this model actually fits really well. So you see we have a non-significant chi-square. So wowie, it's really nice, right? Beautiful. And then look at, we get the usual test statistics right here. This is significant. Seems to be a decrease over time, right? Decrease in smoking over time. That's what this is showing. And I think that's what we saw, right? Kind of when I first pointed out these values. But let's take a look at adding some predictor variables, right? Because wasn't I saying that this is getting larger over time, more or less, right? Yeah, this is a large data set. Okay, so what did I want to add here as predictors? Add baseline depression. Okay. In addition to the predictor variable, run latent growth for smoke. In addition to prior predictor variables. We're going to add the same one. So gender, baseline, smoking, Hispanic ethnicity, anxiety. I'm going to not add anxiety because anxiety and depression tend to be so strongly correlated. I'll just keep one of them in there. I'll take anxiety out and use depression instead. And then sensation seeking. All right, let's do all that. Excuse me. So again, so the variables I am using here are sex, not HISP, depress one. What else did I say? And sensation, right? Sensation. Okay, so I'm not going to do anxiety, sex, not his. We're not going to do lunch. Let's do lunch. No, we're not going to do lunch. And then here we'll do intercept slope on. Let's just start with sex, not HISP, and depress. We know that depression is related to smoking. So, and it should remain like that here. Let's take away sensation seeking at this point, because otherwise it'll model it as like a floating variable. So these could be our control variables, right? So let's just see what happens with these, right? And a lot of times they're more strongly related to baseline and then they are to rate of change. So let's run this. Uh-oh, something went wrong. What did I do wrong? Oh, depress one. So I did something. I wrote duress one rather than depress one. Where did I do that out here? Try this. All right. So here we get our output. I think it's weighted least scores mean and variance adjusted. I think that's what that means. Sorry, I can't remember that. All right, so let's look at these. Here again, we have our thresholds. So remember, the thresholds are assumed to be constant, even though they do change, right? So that's how we look at growth, looking what really happens versus what we assume to happen. Warning, the residual covariance matrix not positive definite. This could indicate a negative variance, residual variance for an observed variable. So we take a look at that because that's not good. You don't want to have these kind of results here. So it kind of makes the problem involving variable smoke one. So I wonder what's causing that. So I don't trust results when I have something like that. Because it even tells you there, check the results. It could be, this might mean you don't have a really good result. So I wonder if that has to do with depression. So let's remove this for a second. I just want to see what is causing that problem. So let's run without depression. Yeah, see, I don't have it now, right? So something really related to depression and smoking at time one. Okay, so I just took that out for a second here, but you can see that this model still has a, you know, non-significant. It's the chi-square is non-significant, so it's a good fit. But of course, then we lost depression there. But we'll see what's wrong. And in terms of predictors, this is not none of these predictors are significant, whether Hispanic or sex. All right, well let's see. Let's try anxiety. I wonder if that was anxiety that caused the issue here. And I mean, if we can use that instead of depression, since they're so strongly related, I'd have to do an investigation to see what the problem is there. But I just want to see something that, because I do want to control for the psychological issue if possible. You see, this one didn't cause a problem. Okay. And okay, there's a significant effect. So females are less likely to smoke at baseline. Now, this kind of appeared, it wasn't significant before. Once we included anxiety, kind of released that. And anxiety had a significant effect on smoking at baseline. There's nothing really significant thereafter because, again, our sample size is huge. So this is like, you're not going to use, alpha is 0.1. Now, it doesn't happen at this sample size around increasing our alpha. Let's add the real important variable here, sensation seeking. Okay. Let's see. So we had these controlled. Let's see if this works. Well, you never know. We made up problems again. Problems occur. No issues. All right, so what do we got here? All right, so interesting. Sensation seeking is significant, right? At baseline. So what does this all mean? So we have females are less likely to smoke than males, and that persists across time. So just because you don't have you're looking at this and saying, oh, there's no impact on rate of change. Well, wait a minute. That just means it's persistent, right? So it doesn't change over time, the effect. And sensation seeking is positively associated with smoking at baseline, and that persists over time as well, controlling for the other predictor variables. And then, of course, you'd look at the standardized values, see what we have here in terms of magnitude. Like one's gender is more important, gender sex is more important at baseline than sensation seeking, right? Because it has a higher magnitude, ignoring the sign. Okie dokie, there you go. Beautiful. All right, so what we did was we talked about latent growth curve modeling. I talked about it with a continuous dependent variable and then with an ordinal dependent variable for smoking. I showed you how to run them. I showed you some information about what the model looks like mathematically speaking in a figure as well. And then I showed you how to run it using Mplus. Wow, that was good stuff. I hope you enjoyed it as much as I do. I always enjoy talking when I can about this stuff. All right, thank you. Have a great